Alright, so same. If you want to join Present Live, please scan the QR code, and so that we can have the different version of a language. So that's it. Maybe no more students want to join. Therefore, let me start. Well, today we will already have the summary of TCP congestion control. So first of all, we have the stats. Well, think about the slow start. Do you still remember slow start? Alright. And also congestion avoidance. Right? Do you still remember congestion avoidance? And also fast recovery. Alright. So same. Slow start, congestion avoidance, fast recovery. You can share some description for the three items: slow start, congestion avoidance, and fast recovery. And right now we want to have the specific description. Well, slow start here. This is the initialization. And initialization, we set congestion window to 1 MSS, maximum segment size. And threshold, SS threshold, we set it to 64. Alright, set it to 64. If you don't like it, of course, you can have the other possible value. But right now, we already have 64 kbyte. As for duplicate egg count, of course, right now, no, so set it to 0. Well, initialization, we have the congestion window, set it to 1. And SF threshold, here we have the value. Well, this is the initialization. And once we have a duplicate egg, of course, we increase the duplicate egg count. Alright, so we have a double plus here. And how about timeout? Timeout right now, we set SS threshold to a half. Alright, if we have a CWND and then cut in half, and then we have the new SS threshold. And because of slow start, so here, and also because of timeout, so here we set congestion window to 1, and we reset the duplicate egg count to 0. So you can check same for timeout, timeout, and timeout. Alright, so we have a timeout here. And in fact, we have a timeout here. Alright, so for all the timeout, we have the same setting. Well, next one, how about if we have a new egg? New egg, then we need to increase CWND, right? So increase it. And because of a new egg, so of course we don't have the duplicate egg, so set duplicate egg count to 0. Alright, so after now, about the slow start almost done. However, have the final one, this one. How about if we have 3 duplicate x? 3 duplicate x. Then we need to go to the fast recovery. So here, fast recovery. Same, SS3, set it to across here. Duplicate x. So same, we have the congestion. So of course, the threshold set it to a half. However, congestion window. Previously, we have the discussion. Congestion window cut, but right now we have the extra 3. So I have a different color. In fact, we have a congestion window cut in half. So sure, we set it to SS3. However, not exactly SS3, plus 3. So we have the extra part plus 3. So that's why I emphasize in blue. And so that you will notice we have extra 3. Alright. So after now, check it about slow start and also pay your special attention to this one. SS3 plus 3 for the fast recovery. Why we need to have for the extra 3? Because of duplicate count is equal to 3. So we think we allow the mode fast recovery can have 3 mode MSS. So that's why we have plus 3. Alright, so first of all, we talk about slow start. That you have 1 minute to check. Alright, so you can discuss it about slow start, and if any question, you can let me know. And you are free to discuss, of course, just take it easy and talk to your neighbors. And before this Wednesday, I planned that you have a file, and that file allows you to have these. Before this Wednesday, I plan to put a file regarding to this page 5. This one for your group. However, I try to ask you to have your name, possibly your photo, and your student ID, right? Name, it doesn't mean you need to have the full name. Perhaps you just have the name. The first name. All right. So I plan to have these, and you can print so you can have a page like this. And next time, if you have it, so I can tell you easy. So for this purpose, I plan to have a file, and you can print, and you will have your own page. Well, why not? Let me make sure. Any question about slow start?
I have a question about what you said about that.
I mean, this one, but you have your own name and possibly your photo and the user ID. Why I ask you to print it? I will not have file, but you change it to your name, user ID, your photo, please. And so that I can call you easy because you have name on this one.
Oh, when will we have this?
tutor can identify easily. So understand these? Alright, so I will modify and so that you can modify that one. Or maybe I ask the tutor to have for the sample file. And it's really easy, just put it and so you will have it. But change it to your name, your student ID. And possibly if you have a photo, you can put your photo on this. I call it your page. It's an enlarged page. Well, so let me check you again about slow start. Any questions? Well, if no, of course, pay special attention to these. And next one about about congestion avoidance. Congestion avoidance. We still have one I didn't mention. This one. Congestion window larger than or equal to SFH. Then we need to change the state to congestion avoidance. So this one previously I didn't mention. So here we need to change if we have a congestion window greater than or equal to SFH. Alright, so these are the possible actions associated with the slow start. And next one, congestion avoidance. Congestion avoidance, then look at this, timeout, right? Same, so it won't be necessary to mention this again. And duplicate add, sure, increase. And the same, 3 duplicate add. Right, so go to the fast recovery. And this one, if we have a new act, for slow start, we should increase congestion window by 1. But this time, because we have the linear trend. Right? So linear trend. How to have the linear trend this way? Alright, so why we have these? MSS multiply this one. And this one, finally, we use this to share. So congestion window equal to MSS multiply this. Right? So this one, somehow like we have this. MSS multiply this. Alright, so this one, CWND over MSS. What that means? This one, MSS, so that we have integers. Integer means currently the CWND not in bit or in byte. This time, CWND in segments. For example, here we have 8 segments. Alright, so 8 segments, we just have, for example, we have 8 segments. The goal for us, we need to reach 8 segments. But just 1 over 8. So once a new 8, you increase 1 over 8. And so that 8x, and then you will have 1 MSS. So this one, finally, you will have the linear trend. Even the linear trend not simply equal to our previous linear trend, but this way we can have the approximate linear trend. Alright, so this one somewhat different from our previous discussion, but still we use this way to have the linear trend. Well, same about congestion avoidance. Check it. Any questions for 1 minute. So of course you can discuss freely, and so that you can share possible learning experience each other. So let me share any questions. So first of all, let me nominate one of you. Marcus? About the linear trend using this way, is it okay? Maybe. And Ken? Linear trend here, use this way to have a linear trend. And Owen? Linear chain. It's fine for you. So that's why I asked you to have your own page, and it will be easier for you to nominate maybe some of you. So I will ask the tutor to prepare one sample, and you need to change it to your name and your photo and your student ID. All right, so this is congestion avoidance, and finally fast recovery. Fast recovery, same timeout, right? And how about duplicate egg? It's a special treatment. For fast recovery, if we have a duplicate egg, because of a fast recovery, we still allow the congestion window to increase. Why? Because we need to have a fast recovery. If you have maybe some limitation, then it won't be okay to have the fast recovery. So for this case, this time we increase the congestion window directly and allow the packet to be transmitted. So this one we have for the special treatment. And next one, how about new act? If we have a new act, then we set congestion window to SS thresh, because previously we have a +3, but right now we set it back to SS thresh. All right, and because of a new act, so we will reset duplicate act count to 0. All right, so for the fast recovery, is it okay? Previously, you already know, if we have a 3 duplicate act, then we will enter fast recovery. And once we enter fast recovery, so of course we need to retransmit about the congestion window. Should we confine to some specific limitation? No, we still allow the congestion window to increase once we have the duplicate act. Well, that's it for this. I think that's okay for you, right? Well, finally, if we have something to keep in mind, this one. If we have a duplicate act equal to 3, this one, not the same as our previous discussion. We set congestion window to the current window, but +3 for the fast recovery. All right, so this is a summary for the TCP congestion control, because it is really important. So I mentioned this for all of you. Well, about this, any questions? Well, if no, later we will have an example, and that example partly rely on this diagram, and so they can have the possible answers. And also remember, Maybe that's night I send you one problem for our thin pair shell, right? Why? Because we have the leading time, and later I will ask you to have a really short discussion, and then you have your answer. Well, later we will have it, but before we go, let me have this for you. Check it. If you still have a question, you can pose your question here, and so that I can re-explain, and so that you can understand. So set it to 2 minutes. And also we have quiz number 2 this Wednesday, and likewise we have three problems there, and allow you to have 20 minutes near the end of the class on this Wednesday.
What's the range of the
Range actually I already have on line group, chapter 2 to chapter 3, and maybe just one of you failed to join, but you need to notice the messages on our line group. And of course, I already have the 2 topics for our thin pair shell partially will be covered today. So I ask you to check it in advance and also partially prepare the answers, because I will already have a few minutes only. So it's really short discussion, but the question is quite long. So that's why I ask you to check it in advance. If you have a question, you can check our line group, and so they will have the problems there. All right, let me measure. Not finished, raise your hands. Okay, so let me go to the next page. Same this one for 2 minutes. So let me make sure. Not finished, raise your hands. Okay, keep going. So let me check again. Not finished. All right, so let me continue. Well, we just have a linear trend for the current TCP, congestion control. this one, do you think it will be fast to reach the possible rate? Maybe for some of our researchers, they don't think so. But in the past, for a quite long time, we use this version, AIMD. However, we can have a new version called cubic. And cubic uses a different way to have the way to probe the possible rate. So how to probe? We have some description. Linear train, we still think not so fast, so we change the train to a new one this way. How about this one? Not linear train, but something like we have, it doesn't mean the exponential train. But something like we have the exponential, but finally we can reach the possible rate. Well, so because of this, so we will have the classic TCP. Classic TCP, that says we use AIMD. So here we have AI. But the current one we call cubic because of a cube. The term of a cube, so we have a cubic this way. And so then this version we call TCP cubic. Alright, that's it. So if we don't like AI and B, because AI, even we have AI, we don't think we have the faster way to reach the possible rate we can reach. So we change it to the new way. If we change it to the new way, then we call a different version, TCP cubic. And how to do? Here we have some description. And we have a parameter K and something else. I go through quickly and then you have the check. We have some estimation of K. Before K and beyond K. Actually beyond K. Something like this is K. Before K we have this, but beyond K we have exponential trend. Why beyond K we have the exponential trend? Something like we have a slow start gain. Alright, so there you have this idea. And you can check the description and so that you know, well, we will follow this. So we have K to have a point in time and reach W max, right? This K actually, it is the estimate time instant. But after that, well, I expect to reach it, but finally we don't. If finally we don't, then we can increase exponentially fast again, like slow start. So this way we have the total version for TCP cubic. Alright, and here it says because of this one, function of a cube, and so that we have a cubic, the name. Well, that's it. So this is a new version. And this version, I just let you know the concept. And where we have this version, Linux and some other possible service, because we think it will be a faster manner to reach the stable state. So we can have the proper way to probe. So that's why some of for example, the system Linux or some of the other service prefer this new version. Alright, and next one we talk about bottleneck link. Alright, so bottleneck link, actually we know, well, why have a bottleneck? So suppose, for example, congestion, so it will be the bottleneck link. Bottleneck link. Alright, so this one I think is easy to find. If we have a bottleneck, and then how to increase the rate. This is the concept here. So we want to know this. We have the rough estimate we know RTT, and also we have a CWND, so we will have a value. Here, this is a minimum value. If possible, we can find the minimum value, and using the minimum value serving as a reference value. So that we have this version, delay-based congestion, a TCP congestion control. We base on this minimum value and the CWND, and we will have the ratio. Based on the ratio, if we have the ratio, near the ratio, we can increase the rate. Or otherwise, we decrease the rate. Why? Because we cannot reach it. So something wrong. So we need to decrease the rate. So look at this. We have the rough estimate. All right. So the rough estimate, the current bytes over these RTT. If we near this one, we can increase. If no, far below, and then we decrease. Look at this, decrease. Right? So very close, and then we can increase because we think no congestion. Or otherwise, why? We set it, but we cannot reach it. So it should be congestion. Because of congestion, then we increase CWND. If we have this version, delay-based TCP congestion control using this concept, then we will have the two cases. Very close, yeah, allow you to increase. Far below, and then we need to decrease linearly. Well, this is the actual version we call delay-based TCP congestion. Well, then you have 1 minute to check this. Specifically, this one first, and then here. 1 minute to check it. And sure, you are free to discuss with your neighbors. So this is a version delay TCP congestion control, so you can check it. This is it okay? Any question about the current version, delay-based TCP congestion control? Well, if it is okay, then we continue. And up now, we have the TCP congestion control to increase the rate, to decrease the rate. And in fact, is it possible to set the notification? Yes, we can have the explicit congestion notification so that we have the shorthand ECN, and so that we can have the network assisted congestion control. This one we just said sender or receiver know the status and set by the routers. So see, we can set it and enable the ECN. Alright, enable the ECN and so that we can allow sender, receiver know, yes, we have the congestion. And this way, so this way, mention we have a congestion in the datagram, then we call this is the notification, and this is the explicit congestion notification. And in fact, we set it to this. All right, so for some details, you can check it. Because of living time, so I don't know, yes, we have a way, and so that we can have the explicit congestion notification. Well, that's it. So if I wish that send a receiver node, currently should we have a congestion? If yes, we can use network assisted approach. And we just mentioned network assisted approach can apply ECM, specifically ECM by TCP. Well, that is the congestion notification. And right now we check fairness. What it means, fairness. If we have a TCP connection 1 and TCP connection 2, and possibly go through all of the routers here, specifically check. How about the first router? If we have a capacity R, should we have the same capacity shared by connection 1 and shared by connection 2? The answer is yes. And why? Why the answer is yes? We gotta know TCP fairness. And so that we can have that. Therefore, this is a goal. Fairness goal, if we have k sections, and so that we should have the rate shared by each section, R over K. So, is it true? Why we have this? Here. And I go through quickly. This one is AI. Alright, so we check for one connection, and here we check, example, connection 1. Likewise, the phenomenon can be observed similarly for connection 2. So right now, we assume this is connection 1. We increase the rate, but finally, we have a loss. Loss event, then cut in half. Is it true? Cut in half. For example, currently we have a value here. So cut in half to the point here. And because of AIMD, so what happens? We will continue AI and cut in half. AI and cut in half. So finally, we will have a trend, this one. Well, we have several AIMD, but finally it seems to be we will have this way. Well, finally, we approach this AI. And if we have this AI, then connection 1 share half of the bandwidth. And likewise, this phenomenon can be applied to connection 2. So same connection 2 approach this one to have the equal bandwidth share. Well, because of this, so we can claim TCP will have the equal share if we have same or identical sections of TCP. Well, that's it. So this is the fairness of TCP. About this, about the application of AIMD to the current connection 1. Any questions? Allow you to have 1 minute to check it. If any questions, sure, raise your hand and let me re-explain for you. So is it okay if we consider two TCP connections or TCP sections, and so that they will share the bandwidth in an equal manner? And likewise, we can use the concept the current example to the case of K section simultaneously. Well, is it, any questions about this? Failed TCP bandwidth sharing. Well, so the answer is yes. Alright, it's yes. And so that here, we consider these. Families and UDP. Because of the families of TCP, so if we have a multimedia, then we will have the equal share. But sometimes for the multimedia, we don't want to do so. So that's why we will choose UDP rather than TCP if we have a multimedia application. Alright, so we will use UDP. And we didn't know this already. And why we mention this again? Because right now we have the families for TCP, but should we have the families by using UDP? No. So that's why we will use UDP if we apply multimedia applications. And if we use TCP, and because of families, but you expect to have more bandwidth, what to do? In fact, we can allocate more connections. For example, right now we have 9 existing connections. And how about one TCP? And so that it should be 1 plus 9, and this one share these. So 110. Alright, and how about if we have 9 already? But you have 11, and so that share 11, and so that approximately we have these. So first case and second case. So that says because of failed TCP, you can have more connections. More connection, then you can share more, and that's it. I think it's easy, so let me go to the next one, this one. And right now, we ask you to apply our previous discussion for TCP slow start. Slow start, congestion avoidance, and something. And so that we have these. This problem, I think you can, I there you have, maybe that's nice. And right now, there you have time to fill in, and so that you have the answer. I collect the answer for this one. So take a picture if you don't have it. Or maybe right now you have the answer already, so you can key in immediately. Of course, if you still need to have the discussion with your neighbors, sure. At this time, about neighbor, you can find your usual partner. So this one, first page, we have a problem A, B, C, D. And E, F, G, H, I, J. And this time, because of limit time, I already have the answer and key directly. And later, if any question, we can nominate some of you to share. But right now, take a picture for the second part. Alright, so this time I changed the way to collect your answer directly. Because I already have the problem, and this time I already have 5 minutes. So you can continue and key directly. And this time you just have the usual partner. So mention your usual partner. And if you want to have the discussion with your usual partner, that's fine. And keep going. So we allow you to finish it to the start of the second class. Or maybe here almost all of you finish it. If you want to take the rest, go ahead. Solution to you. So you need to get this done within 3 minutes. Even if you don't have the complete solutions, but it's just saying the possible answers to Paul algebra. even you don't have the complete solutions. Alright, maybe in a few seconds. Alright, at this key in sum. And sorry, at this you will receive 3 points. If you have the almost accurate answer, then you can receive 5. So it doesn't matter, just let us have your answer immediately. So final 1 minute. You just upload and don't care about too much. So get it done and don't think too much. We still have 10 seconds. Alright, click on submit. Alright, click on submit and that'll check the answers. So let me check. Finish submission. Okay, so that'll check the answers, sorry. This one. And for A to K, take a photo. A to K, take a photo. A to K, take a photo. Alright, let me have the fact to check with you. Today, group 1, only you. Oh, okay, you serve as a presenter. You check some problem A. Correct answer by you or not? And good too. One of you check your answer. Some problem B. Correct answer from you or not? And C from group 3, D from group 4, E from group 5, F from group 6, and G from group 7. It's really easy. I just want to check. You have the correct answers or not? Alright, just one. And good one. Of course, you need to let the tutor know you are the presenter. Very cool. And next time, if you have the page, and then I will ask you to take a photo. And slowly it will be easy. So, first of all, good one. Correct for your problem. Okay. Alright.
Correct.
Okay, thank you. So correct by good one. And good two. Who will be the presenter? Correct or not?
Yeah, correct.
Okay, thank you. And good three.
Correct.
Good. And good four. Who will be the presenter? Choose one.
Correct.
Okay, thank you. And good five.
Is correct.
And good six. Who will be the presenter? So let me know your answer, correct or not.
So it's correct.
Okay, thank you. And good seven. This time, who wants to let me know your answer, correct or not?
Correct, but I want to ask one thing. That these questions have it has to K, but it only comes to J. It doesn't have K, so I think the version is not right.
Alright, so maybe something wrong with the release solution. That's why I want that copy. IJ. Oh. So maybe the index not correct. So I just checked the first 7 subproblems, and you can check the remaining. And the other thing you will check is this time I know the status, so I go to the next one. And for the index, maybe something wrong, so you can correct it. Or maybe we have for the actual, at least if you have for the redundant one, you can remove it, but I don't think so. So this is the reference solution to this problem for our thin pair shell. And in fact, this one is really important, so you need to know. And next one, evolution of transfer layer functionality. This one I will go through quickly. So we have a TCP UDP. In the past, only TCP and UDP. In fact, we need to have more. And how to have some possible evolution. Alright, so here we have all these. And in fact, we will have HTTP version 3. Here, maybe I call it quick. QUIC quick. And in fact, HTTP 3 quick. This time we don't rely on the TCP, we rely on UDP. So actually, using HTTP, we use TCP to version 2, but to version 3, we use UDP. Right? And also, we move some service to the application layer. So this is the new version, quick. Alright, and something to be done by this quick UDP, so we call quick. And for this, I think for your reference. And here we have the new connection establishment for quick, because based on UDP to have a quick. And sorry, we have some version like TCP to have a connection establishment. Well, so this is a version, new version 3. But right now it's the version HTTP 1.12 and the others. Well, I mentioned that quickly. We may have for the new version. The new version may be not the past UDP TCP simply. Possibly we may move some function to our to our application layer. And here, this is a summary. And thing, just take a look, and then we can go to the next one. So almost done, but we have some additional slides. Additional slides that have some more detail. For example, that have detail about finite state machine of standard. And if you follow the finite state machine of the standard, then should we have the timer when we have the transmission for the packet? No. We just maintain the timer for the oldest one, but the time is not exactly associated with that segment sent. Alright, so you can check the codes here. Even the codes here, perhaps you need to have the slide multiplication, but I think something like this. Alright, so you can follow the concept to know some of the possible implementation of go back in. And in fact, in the past, I asked students to pass out the FSM here to have the diagram if we have some possible message exchange. Alright, so this is the extended FSM for the standard. You can take it for reference. I don't go through in detail, but just let you know. And likewise, we can have go back, but this time we have the receiver side. And quickly, I let you know about buffering. Go back, should we have the buffer size? I let you have one. One for that oldest one you want to maintain. And in fact, if you think, well, that one, it doesn't mean we have any extra buffer. So you can mention no receiver buffer. But I don't have one to count the oldest one at least. Alright, so this is the receiver extending FSM for your reference. I think sometimes we have the pseudocode, so I assume all of you can understand the pseudocode. So I go through quickly, then you check the details. And in fact, you can check all three classrooms and so that maybe I have some possible explanation on the two extended FSMs for the sender and for the receiver. And in fact, this is a simplified PCP, taking care of the sequence number and X. Alright, so this version you can check it for sure. And in fact, this is the simplest idea, and so you will know we can have the retransmission, and if we have a timeout, and also how to maintain the act, because we have the cumulative act for TCP, like go back N. Well, this one, in fact, not the same as the previous one. It's just that you have the possible connection establishment for TCP. And we will have this one server and this one client. And so that these are the procedure for server and client. I put them together. So this one, in fact, it is not the finite state machine for connection establishment for the client side. This one for both sides, server side and client side. Likewise, you can refer to the free classroom video and so that you can know, yes, we follow the possible state transition so that we have the connection establishment for server and for the client. And this is a way if we close it. So right now, we already have a client, and we already have a server. So really special one should be these. Client has to close. But for the years, we receive it, but it doesn't mean we can receive it and then we close it immediately. We need to wait for a random time. Why? because maybe we reserve the time, maybe something to do from some message of the server. So we should have the spare time, and the spare time we will have a random time set it to 2 max segment lifetime. And so that after that, then the client can close it. However, for the server, it's sure because it asked me to close it. All I can do, and then I do it so that once I receive it, then I can close it immediately for the server. Well, I just emphasize for client and server. Server can close it once we receive app from the client. But for the client, no. It should wait for a random time and finally close it. So that's why finally we will close a bit later because we need to wait the extra time. Alright, so this is a connection closure for client and for the server. Of course, this time, this is closing a connection by the client. So of course, initiate by client. Well, this one talking about calculation of throughput. We definitely have for the exercise as well, and to follow the current description to have the detailed idea so that you will know the possible answer to those questions. And here, if we have AIMT like this way, what is the average TCP throughput? Sure, it should be this one. And likewise, if you have a different way to increase, and then you need to well take care of those. Well, finally, we have an exercise. That exercise must be that you have for the derivation, and the derivation that you have for the version. TCP throughput should follow this form. If we have this form, we have loads, L. If we want to have a really high bandwidth, for example, 10G, and then what is the loss rate? Sure, because you want to reach really high throughput, so of course you should have an extremely low loss rate. Alright, so follow the current formula, of course, the current TCP, we can achieve it. Of course, we should have the low loss rate. Well, if we still follow the current version, we should have the really low loss rate. So that says, if we want to have the beta 1, we expect to have the beta version of TCP. And so that the beta version of TCP can provide the high-speed transmission. And that's it. So I go through quickly for the additional slides. The additional slides, in fact, just let you know more if you think, yes, you need to know more, and this way, we already have the extra slides. And in fact, the extra slides contain in the normal slides of the classroom videos, right? So we do not reserve all the additional slides to the end of the discussion. In fact, we allocate the slide to the proper places, and so that we have the proper discussion at the right position. Well, that's it. So if you still need to have a more detailed discussion, you can refer to our free classroom video so that you can know more detail. But for this, I just go through quickly. Did you know? Yes, we have some extra slides, and you can check it. Well, about the extra slides is okay. If you still think you want to know more, sure, I recommend you to check my free classroom video so that you can know. Well, that's it. So almost done, but I already have the delay modeling of the TCP slow start. Yes, I asked you to check it, but I'm not sure you checked it already or not. Well, in fact, we have one problem associated with the modeling. in our textbook. Even our textbook don't mention this, but that question needs to rely on the knowledge or the background here. Well, delay modeling, let me check. So before I go, let me ask you to have the message on line group first. So previously we have 7 presenters. Don't forget to send a message on our line group so that the TA knows you are the presenter, so that you can receive a bonus of 2 points. So first of all, for the 7 presenter, send a message to the line group. And next one, let me check. Anyone check the classroom video about the slow start? If yes, raise your hands. Well, no. Okay. Let me make sure again. Anyone check the delay modeling using all 3 classroom videos? Okay, no. So I should go through, but I will go through a bit quickly because I assume you should check it. If you still need to check more details, you can check that video. Or maybe you can review our recording video again to make sure you can understand what I talk to you. So delay, sure. The waiting time, and we want to let you have the way to calculate the time regarding the slow side. So this is a question we set. How long does it take to receive an object from a web server after sending a request? During the phase of a slow start. Not for all of the stages, only for slow start. Alright, so that's why I gotta have a topic. Delay modeling of TCP slow start. Well, so because of that, we already have a slow start. And we consider data transmission delay. And also we consider the TCP connection establishment. Alright, so up now we have all the factors here. And ignore the others. So of course it should be the delay modeling associated with slow start. And of course, before slow start, we need to have the connection establishment. And also, we should consider transmission delay for sure. So, of course, we consider these factors. So that says delay is influenced by the 3 factors. And we will have a notation. Take a picture first. We have R capacity. We have S to denote MSS. We have O to denote the object size in bits. And the no retransmission. We assume nothing wrong. And this is the actual assumption. Nothing wrong. If we have the perfect transmission, so that we don't have the retransmission. And about the window size, previously we can have the congestion window size, right? So if we have the congestion window size, we don't have the fixed rate. Instead, we have the variable rate, but later we will assume we have the fixed rate, and so that we have the dynamic window size because of the dynamic congestion window size. Well, up to now about our assumptions here. Check it for 1 minute. And later we will apply all this to have the description, to have the modeling. If any questions, sure, raise your hand to let me know, and so that I can re-explain for you. is to have the following discussion. First of all, fixed one. And fixed one, we assume it's W. Alright, so it's W here. So connection establishment. So we have two RTT. And we consider the first case. The first case says this. This one larger than this. It's really special. RTT plus 1 transmission delay. Why? Because of this. RTT and 1 transmission delay. Alright, or maybe this one, 1 transmission delay and RTT. So window size greater than that one. Then what happens? It says if we have this condition, then no waiting time, no idle time. Because of no idle time, then the current calculation should be 2 RTT plus the transmission delay simply O over R. Well, at this moment, maybe not really easy to tell why no gap. But we can use the second case. The second case to illustrate explicitly, we will have a gap. Why this time we can see the gap? Because it's a case to have the gap. This time, this one, smaller than 1 RTT plus 1 transmission delay. And so that we will have the gap in white. So here we have a gap. And the idle time. But why we have the idle time? Connection, so we have 2 RTT, set it to a constant. And then we have this 1 transmission delay and 2 RTT. So we will have an egg. Once we have an egg, this one, and then we can have the next transmission. Right? But right now, we think because of a server send the segment and wait the egg. So, send the segment and wait for the egg. We will have a time, 1 RTT and 1 transmission delay. So this is the time required. 1 segment plus RTT, so that we expect to have egg. Once we receive the egg, then we can send the next segment. However, if the current WSS smaller than the time smaller than this, then we won't have enough segment for transmission. So this time we will have the gap. And how about the gap? The gap should be the current time minus the window size over the capacity. So that is the gap. And right now we assume we have K gaps. K windows. So that we have K times of window. So that we will have K minus gaps. So that we have K minus 1 immediately. Well, this is a current relation. Specifically, you can pay attention to case 2 first. And then you will understand, get back to case 1. Then you will understand, sure, if we have transmission delay plus RTT minus this one, it's a negative value. It says no gap. But this time we have a positive one says yes, we have a gap. Right? So about the gap, take a picture for the current slide. Take a picture for the current slide. All right, and compare with this one. Then you will totally understand this one, no gap. But the first one, we have a gap. All right, now you have 1 minute to think about this, along with your photo and this slide. And so that you can understand the first situation. We have the fixed window size. 1 minute to discuss with your neighbors. Well, so first of all, about the current deviation, fixed window size, we have 2 cases. Any questions? Let me check. Ken? Okay. Owen? Okay. And mothers? Should be okay, right? Perhaps you don't like the derivation, right? Maybe you don't like the derivation, so that's why you think, oh, well, that's okay. Okay, sure, I got it, no problem. At least we have the derivations. Well, next one, this is the dynamic window size. We expect to have a formula. So here it's a formula. And later we want to know why we have a formula like this. And before we go, yes, take a picture for this page, and later you can check. We can have it. And also we have the actual one, P. P set it to the minimum of Q, O, K minus, and K minus 1. And Q, it is the definition here. Number of times the server idles if we have the object with infinite size. What it means for Q and what it means for P, later we can know. Currently we have K. We have the number of windows. Even we don't have the fixed window size. But times of windows open. So K, it should be times of windows open. And the Q means this one, idles. How many times of idle? And so that P set it to this one. And once we have this one, then we will have the formula to have the latency, to have a delay. 2 RTT, we know it. OR, we know it. We don't have any gap. But finally, we have the gap. If we have the proper parameter, so this one should be gap. Gap means we should have idle time. Well, I can say, but because of some smaller window size, so we don't have any extra segment to send. So of course we should have the gap. Well, the gap like this version. Because slow start, so we start from window size 1. Then window size 2, then window size 4, then window size 8. Is it okay? Slow start, right? Because of this, so we will have the smaller window, then we have the larger window. And based on the previous derivation, if we have the fixed window, window smaller, then possibly we have the gap. Window larger, then we won't have the gap. So you can see when we don't have the gap. If we have the current example larger than 4, then we won't have the gap. Why we won't have the gap? Because we assume one transmission delay plus RTT smaller than 4 segment transmission delay. However, we won't have the gap if we just have 2 for the window. Here, we just have the assumption. Alright, so it's a reasonable scenario. Smaller one, then we won't have the gap. Larger than, maybe larger one, then we don't have the gap. So here, we have gap. If we have a window lower than or equal to 2, but larger than 4 or equal to 4, then we won't have gap. Well, look at this. We have this example, the scenario like this. 2 RTT won't be a problem. And here, if I want to find P, can you have the P? So currently, we have a K is windows open. So how many times of windows open? 1, 2, 3, 4. So it's 4 that says K equal to 4. So let me check K equal to 4. If it's okay for you, raise your hands. K. Currently the example K equal to 4. Is okay? K equal to 4. If yes, raise your hands. No? Let me know. Ken? Okay for you? Owen? Okay. And anyone not okay for the current value K? Yes? Have some problem with the current value K? Okay, no, right? So, okay for K. And why Q equal to 2? Idle. So this one idle. 1 and 2. And the window is extremely large. If we have the large window, then even larger. So we won't have the gap. Only 2. So here Q equal to 2. If we have the extremely large object size. So Q equal to 2 is okay for the current example. Owen? Okay, right? Ken? Marlis? Q equal to 2 for the current case. So we have the current setting K and Q. So finally, what is P? P for the current case is equal to 2. But sometimes it should be determined by K. So the current case determined by Q to have the value of the P. So we will have the result easy. So it's just a definition. P equal to minimum of K minus 1 and Q. So according to the definition, we should have 2. Well, this page we have these. Right now, we want to have the derivations. How to have the derivation? Look at these. The part in colors, it's the transmission delay. And we have the connection attachment. So we have 2 RTT. And finally, we need to account the gap in white. The gap in white, that says is idle time. How many idles? The idle time determined by the current parameter P. 1 to P. We have the P times of idle. Why P times of idle? Based on that formula. Because if we have a K window and if we don't have the idle time smaller than K minus 1, of course that one should be determined by K minus 1. Or otherwise it should be Q. So that's why we have that formula, P equal to that. And finally we use use the notation simply P to indicate number of idols. Alright, so number of idols. And number of idols, how do you have these? The first one, it should be to open window for the first time, to open window for the second time. Open window for the first time, we will have the window size W. Window for the first time, and it should be this formula. Is it okay? Window, first time, second time, follow the current formula. 2 raised power to I minus 1. Can you accept these? Because for the first time, it should be 1. So 1 minus 1, we have a 0. 2 raised power to 0, it should be 1. And the second one should be 2. 2, it should be 2 raised power to 2 minus 1, so of course it's 2. So the window size follows this one. And also, previously we have these. Transmission delay plus RDT minus these. If we know, yes, we have idle. So, this is a way to have the idle calculation. Finally, according to the derivation, we have these. You can check it. All right. So I then have 1 minute to check. Window size WI for the first time to open, the I time to open. And finally, it should be these. 2 raised power to K minus 1. Even I then have I, you can have K. And so that we can have the delay, follow these. About the derivation, finally, okay or not? If you want to apply the formula, sure, you can apply the formula. But normally, should we apply the formula? Maybe no. So later, I already have some other way to skip the formula. So let me measure for these about the formula derivation and equations. So modus, no problem. Good. Can and hour. Okay. Let me choose one to measure. Alright, so if I want to apply the formula, just follow the idea. Because we have the previous discussion to have the fixed window size. 2 to K minus 1 is fixed window size. But given K, however, K may change. So of course, we follow that concept. We can have the derivation for the dynamic one. Because dynamic one follow the formula here. Alright, that's it. So this is the derivation. I think about the formula, no problem. And later one, we should already have the parameter finding. How to have the K? So K is this way. we want to have the first window, second window to k minus 1 if we have the given k, so that this one can cover the object. Alright, so we will find the minimum k to cover that object. Then that's the time to open the window to cover the object. And so that we have this one. Alright, so this I think just this one. Alright, you can have the division. And how about Q? Q is easy. Q we should allow Q to be passive 1, 2, 3. When we can have the largest I to have a positive value here. Alright, we can increase I until we have the minus 1, but get back to the previous one, so that we still maintain the largest one. Why the largest one? Because we should have a positive value, so that we still have the gap, still have the idle. So you can follow this formula. And this formula, what it means? This formula says it's the idle time. Open during the ice window. Still we have the idle time. And the idle time should be positive. Then it's a real idle time. Finding the largest I, and then that is the value for K. Alright, take a picture for this side. And start to think about this. And also you can refer to my free classroom video, and so they can understand that. And finally, we have some description. If you can combine some discussion in chapter 2, and so that we have the formula for all the times given here. I skip it, and even we don't finish it this time, still check the bottom. And this Wednesday, I will ask you to key the answer for A, B, C by considering the current example. But the current example, if we have all these, and if know the gap, so should we memorize the formula? In fact, no. Should we memorize the formula? No. Let me mention this quickly. What is a gap? What is the first gap? It's one transmission delay plus RTT, right? And also minus 1, so it's RTT simply. So we can find the gap exactly, no problem. And you can consider the second one. What is the gap? It's S over R plus RTT minus, this time 2 minus 1 S over R. So this is window size 1. This is window size 2. So the gap here, it should be RTT minus 1 transmission delay. If you know the gap, follow the formula. S over R. So here, gap I, follow the formula. S over R plus RTT minus WI S over R. So this is a gap. First gap, second gap here. And then you can find first gap, it should be RTT. The second gap should be RTT minus 1 transmission delay. If we have a scenario like this, well, we know the gap in white. So should we memorize the formula? No. That's it. So if you know this and consider this example, and if possible, the example looks like this. Then, should we memorize the formula? And then we have a hint. Why we have this? S over R plus RTT greater than and lower than what it means. The condition here, that we know which window we can have the gap. But beyond that one, which window we don't have the gap. So we have a case 1, case 2, and case 3. So you can have different cases. For different cases, you should account for the gap. Should we have a gap 1? Should we have a gap 2? Or we only have a gap 1, we don't have a gap 2. So you can minimize the gap to 0 or allow that gap to be 0. So that you can have the time calculation. If we consider the slow start to have the time. Alright, this one, you see? Delay introduced by PCB slow start. So, same is time, maybe not right now, but the beginning of the class this Wednesday, I will ask you to finish this by using 3 minutes. Oh, sorry. This one. You need to check the forward, and this Wednesday I will tell you that you have the answer for the problem A, B, C directly. So I want you 3 minutes to finish the collection for your answer, and try to shorten the time by using this way. So do you copy that? So this time, yes. Last time, only 3 minutes to finish key your answers. Study as this is an exercise